Now that we've been learning about polynomial functions, which are always number one, smooth and continuous in their graphs, it's a good time for us to be able to bring to light something that we call the intermediate value theorem. It's a really important theorem that tells us some powerful results about continuous functions. So basically what the intermediate value theorem is saying is that as long as you have a function, so if f, it has two characteristics. So number one, it needs to be defined, and then number two needs to be continuous on some interval of its domain, so from A to B, then we can kind of say some cool things. So right now I just want to kind of picture or help you visualize what I've written so far. So what we've said is that on some interval from A to B, so maybe like this is going to be the coordinate where A is on the x-axis, and say this is where B is going to be, that the function is going to be completely defined. So being defined means that it's going to have y values that exist for every possible x number between A and B. But not only that, but then it needs to be all connected, right? So you might have like a function where it like, goes like this or whatever, and then entirely on A to B, actually it would be defined because every x is going to a y value on that interval. But it's not continuous because you can see that the pieces are not connected, right? So we need both aspects. We need the y values to exist for every x on A to B, but also it needs to be continuous. So that means that, maybe if you have some graph, whatever is doing whatever here, and then it comes right here, and then you've got to be defined and continuous entirely on A to B. So maybe it like ends up over here somewhere, right? And then keeps going maybe afterwards. So what I need to see now here is if the function is going to connect from dot number one to dot number two, and it's going to be continuous, right? A lot of stuff could happen. Like it could just like whatever go like this, or it might go like really high, come back down, right? But at least it's going to be completely defined and continuous on that interval, right? So because it's going to be defined and continuous, we can say then for sure that to connect from dot one to dot two, or in other words, to go from this y value at f of a to this y value at f of b, we are guaranteed that because the function is going to be defined and continuous, that we have to cross every single y value between f of a and f of b at some point, right? So if it was just a straight line, then we're going to hit every single y value in that little yellow interval, right? But also, like if we go like extremely high and then come back down, whatever, and hit, right? We're still going to hit every single one of those yellow y values, right? We aren't guaranteed to hit any of the y values up here necessarily. Obviously, we are based on the picture, right? But if the line was just a straight line, then of course we're not going to hit those y values, right? So all that we're guaranteed is to hit every y value between f of a and f of b. So basically then, as long as f is defined and continuous on a to b, then what we can say is then f is going to be able to take on every single y value. So every value, and when we say value, we're assuming the function value, so the output value, every value between f of a and f of b. Okay? So that's one way of stating the intermediate value theorem. We sometimes might just call it the IVT for short, right? So we could put this in like other words. So kind of another version that would literally describe the same thing here is we could also say that there has to, as long as the function is defined and continuous on a to b, then what we could say is there must exist some, let's call this x number c, that is between a to b. So some c number that's in that interval from a to b, and specifically an open interval. So we're saying like literally has to be in between a and b, such that the y value corresponding to x equals c is going to have to be like between f of a or f of b. So like one of these is going to have to be f of a, and then the other one's going to have to be f of b. So in some cases, like f of b might be higher, or f of b might be lower than f of a. So just put one of the other on the other side. Nonetheless, moral of the story is that f of c has to be a y value between what f of a is and f of b is. So it's just kind of another version of saying the same thing, that we're going to be able to hit every single y value between f of a and f of b, right? So applying that here, this will be a direct way where we can use the intermediate value theorem and its conclusions. So here we're asked to use the IVT to be able to show that the function f of x equals x to the third minus 6x plus 2 has a 0 on the interval from 1 to 3. So what we need to establish first of all to be able to use the IVT is that our function is actually defined and continuous. So we need to think about this function right here and ask ourselves, like, is it actually going to be entirely defined on the interval from 1 to 3? And then we also need to ask ourselves, is that function going to be continuous entirely on that interval from 1 to 3? So to address that first thing, we would need to make sure that there's going to be y values that exist for every x number between 1 and 3. So if you think about plugging in numbers between 1 and 3 for x, like you can always cube those numbers and multiply them by -6, that sort of thing. So then it's going to be defined, right? We're going to have y values that exist entirely on the interval from 1 to 3. So we're good there. And then the second thing is the graph going to be continuous? Well, the function is a polynomial function, right? And what we know is always true about polynomial functions is they're always smooth. They're also going to be continuous entirely on all real numbers for x. So then, yes, it's going to be continuous. So therefore, we might be able to apply the IVT here. So what we would need to look at then is we would need to look at what the y values actually are corresponding to x equals 1 and x equals 3. To see then like what y values we could actually like hit, right? So at 1, we could evaluate f of 1, which would be 1 to the third minus 6 times 1 plus 2, which is 1 minus 6 plus 2, which is -5 plus 2, which is -3. Okay, so we just figured out that at 1, the y value is -3. Cool. Let's also evaluate at this x number of 3. So f of 3 is going to be 3 to the third minus 6 times 3 plus 2. 3 to the third is 27. 6 times 3 is 18 plus 2. 9 plus 2, which is equal to 11. Okay, cool. So f of 3 is equal to 11. Okay? All right, so what the IVT would tell us then is because f is continuous and defined, right? We need those two things on the interval from 1 to 3, okay? Then what the IVT would say is then f must take on every y value between f of 1 and f of 3. So f of 1 was -3, and f of 3 was 11. So specifically between -3 and 11 then. So we're guaranteed that we're going to take on every y value between -3 and 11. But that specifically can only happen on the interval from 1 to 3 that we're guaranteed. So between -3 and 11 on the interval from 1 to 3. Okay? So because we can conclude that, then this here has to happen. That f has to have a 0 on 1 to 3, because having a y value of 0 is definitely going to happen between -3 and 11, because 0 is between -3 and 11. Okay? So therefore, then we can kind of infer from there, then like it's going to have a 0 and make that conclusion, right? So to help you kind of visualize what's actually kind of happening here, if we were to look at this graphically, this would be the equation for f, and then this is the graph of the equation f. So we were concerned with just the interval from 1 to 3, so this interval of the domain. When we plugged in 1, we figured out that we did get a y value of -3, right? Hence why the point 1, -3 is on the graph. And then when we plugged in 3, we figured out that we were going to get a y value of 11, so therefore, the point 311 is going to be on the graph, right? So, obviously, the graph is completely continuous and defined on that interval from 1 to 3, per that blue part of the graph now, right? So, therefore, there has to be some 0 on 1 to 3. Now, it turns out, right there is where we get a y value of 0, right? It's some decimal number. We're not asked to solve for it, right? We're just trying to verify that indeed we are going to actually achieve some y value of 0 for an x number that's between 1 to 3, right? So that's the power of the IVT and the intermediate value theorem, okay? So here's a couple examples where we want to determine whether we can actually use the IVT to prove that we attain some particular function value. So in this example right here, we have we want to try to show. So we want to try to show, does g of x actually equal negative 0.4 on this interval of the domain, so when x is a number between 2.5 and 3.5, for this particular function, g of x. Okay? Now g of x, you'll notice right here, is like a fraction function, right? Like a rational function. So we would need to ask ourselves, like, number one, is this function going to be defined entirely on the interval from 2.5 to 3.5, right? So can you actually like plug in all of those numbers between 2.5 and 3.5 and always get a real output for the y value, right? So because we do have a fraction function, right, we always want to concern ourselves with the denominator because the denominator should never equal 0, right? So because the denominator is 2x minus 6, right, it could possibly equal 0. We don't want it to equal 0, right? But if you solve for x, add 6 and divide by 2, then when x is 3, then plugging in 3 would make the bottom peak 0, right? And then the y value would be undefined at 3. And that's kind of an issue because 3 is between 2.5 and 3.5, right? So what we can say is like, is the function defined entirely on the interval? No, it's not going to be defined on the interval, right? So right there, we can just stop because we need to make sure that the function is defined a continuous entirely on the interval for us to be able to use the IVT. So like the IVT like cannot be applied right here to guarantee that we get a y value of negative 0.4 somewhere on the interval, okay? So just to kind of help you visualize this, right afterwards here, this is the graph of y equals 1 over 2x minus 6, and you'll see that right here, when x is equal to 3, right, there's a vertical asymptote right there. So clearly, there's going to be no y values that exist when x is equal to 3, right? And we saw that from the equation. So when we look specifically like on the interval from 2.5 right there to 3.5, okay, we were trying to like guarantee that we're going to get a y value at of negative 0.4, which I think actually like might be able to like legitimately maybe happen. I don't know. Well, maybe not. Maybe like, so here's negative 0.4, right? So it actually happens outside of the interval, right? But there might be cases where like actually between 2.5 and 3.5, like it might actually attain a y value of negative 0.4, right? But we wouldn't be able to guarantee it because the function's not defined there at 3, so it's not defined entirely on the interval. And actually even furthermore, right, like it's not even continuous entirely on the interval because this piece of the graph is not connected to that piece, right? So yeah, we're not able to guarantee. And then in this little example right here, we're trying to show, does h of x have a real 0 on the interval where x is between negative 6 to negative 3 for that function h? And if you look at h, it's just a polynomial. So whenever you have a polynomial function like that, it's going to be defined entirely on all real numbers, right? Because you can plug in any numbers for x to get cubed, to get squared, to multiply with a number, right? And polynomial functions are continuous. So clearly this is going to be defined and continuous on R, actually. So then, of course, because it's defined on R, it's going to be defined and continuous on the interval from negative 6 to negative 3, of course. So we may be able to apply the IVT here. Now, if we evaluate h of negative 6, I'll probably want a calculator for that. So negative 6 to the third plus 11.5 times the negative 6 squared plus 42.5 times the negative 6 plus 50. We end up getting a y value of negative 7 there. Okay, and then if we evaluate using negative 3 instead, get a y value of negative 1. Okay, so therefore, because the function is defined and continuous, and then we get a y value of -7 at x equals -6, and we get a y value of -1 at x equals -3, then what we can say is that h is going to take on every value, every y value that is between -7 and -1 on the interval from -6 to -3. Okay, so we're guaranteed for that to happen. What we're trying to do here is we're trying to figure out if h has a real zero, which means to attain a y value of 0. Well, that's not what this says right here, because what that says right there is it only attains y values between -7 and -1, which 0 is not between, right? So therefore, in this example as well, the IVT cannot be applied to guarantee that there is going to be a real 0 on -6 to -3. Okay, so just purely based on the theory, we don't really know for sure if there's going to be a real 0 or not. So if you do look at the function and its graph, we were concerned with this interval from -3 to -6, right? So here's where it got to its y value of -1 when x was -3, and then down here is when it got to its y value of -7, right? So we were only guaranteed that the function is going to attain these yellow y values on the interval from -3 to -6, which it does. Okay, so we didn't know for sure if it was going to have a real 0 on that interval. Now, actually, it does. It actually has 2, but we wouldn't know that based on the statement of the theorem, right? We're only guaranteed to know for sure, like without looking at the graph, that it's going to attain every y value between -1 to -7. Okay. All right, so that is the IVT and the nuts and bolts of what it means, what things need to be in place, as well as understanding, when we can versus when we can't apply the theorem.